Hi guys, so today our lecture is on minerals and mining. So a key topic in environmental science is minerals and mining. And we'll see what minerals are, how they're extracted, and the environmental impacts of mining practices. So this will give us a better understanding of how the materials we rely on every day are sourced and at what cost to the planet. So before we dive in, let's take a quick look at what we'll be covering today. So first, we'll talk about the types of mineral resources and how we use them in everyday life. Then we'll look at how these minerals are processed and the main mining methods used to extract them. And we'll also examine the environmental and social impacts of mining, both locally and globally. From there, we'll explore efforts to reclaim mined land and discuss mining practices. And then finally, we'll wrap up by considering how we can use mineral resources more sustainably going forward. So when we think about the cost of our electronics, we often forget what goes into making them. The tantalum, for example, is a key mineral used in capacitors for cell phones and other electronics. So much of it is mined in the Democratic Republic of Congo, where mining has been tied to violent conflict since the late 1990s. Rebel militias often control these mines, leading to widespread human rights abuses, including forced labor and violence against civilians. So this raises serious ethical and environmental concerns about how our technology is made. In addition to human impacts, conflict mining also harms ecosystems. So as people flee violence, many take refuge in protected national parks, leading to serious ecological consequences. Forests are cleared for firewood. Endangered species like the okapi are hunted for food, and erosion increases around streams. Plus, mining operations often release toxic metals into the environment, polluting soil and water. So this shows how human conflict and environmental degradation are deeply connected. Unfortunately, most tantalum miners in the Democratic Republic Congo don't benefit from their labor. Instead, armed groups often steal the minerals and sell them on international markets. In response, grassroots campaigns have pushed for embargoes on conflict minerals. A peace treaty in 2002 and United Nations led efforts have helped reduce violence, but challenges remain. So, as demand for these minerals continues, illegal mining has spread to places like Brazil, Colombia, and Venezuela, showing this as a global issue, not just a local one. So this image helps us visualize just how many everyday items rely on minerals from the earth. From the aluminum in soda cans to the lithium in laptop batteries to gold and tantalum um, in your phone. So much of what we use starts with mining. Even things we don't think about, like the paint on the walls or the ink in a pen, contain elements that were extracted from the ground. So this shows us how deeply connected our daily lives are to Earth's natural resources. So now let's talk about where minerals actually come from. They're found in the Earth's lithosphere, which is the outer layer of rock, and their distribution depends on both slow and sudden geological processes like plate movement or volcanic eruptions. A rock is made up of one or more minerals. A mineral is a naturally occurring solid with a specific chemical structure and physical properties. Sometimes the entire rock is useful, like limestone, and other times we extract specific minerals from within a rock, like copper and gold. So to access the minerals we need, we rely on mining. Mining is the systematic removal of rock, soil, and other materials to extract minerals that have economic value. So while we often think of metals, mining can also include extracting other natural resources like fossil fuels and even groundwater. That's one of the most direct ways we interact with the Earth's geology to meet human needs. So this slide puts things into perspective. A child born in 2015 is expected to use over 1.4 million kilograms, or about 3.3 million pounds of minerals, metals, and fuels over their lifetime. Most of this comes from materials like sand, gravel, petroleum, and natural gas used in construction and energy. It's a powerful reminder of just how dependent modern life is on mined resources and how sustainable management is so important. So metals are incredibly useful because they're strong, malleable, and conduct heat and electricity. But most metals aren't found in pure form in nature. Instead, they're part of ores or rocks that contain enough metal to make extraction worthwhile. For example, aluminum comes from bauxite and copper comes from cha- chalcopyrite. Mining and processing these ores is how we get the metals we rely on for everything from wiring to cell phones. So once ores are mined, they aren't immediately usable. First, they need to be crushed and washed to separate the valuable minerals. Then comes smelting, a high temperature process where the ore is melted and combined with other chemicals to extract the metal. Sometimes metals are mixed with others to create alloys like steel or bronze, which are stronger or more useful than the pure metal alone. So processing metals doesn't just take effort, it has serious environmental impacts. It often uses a lot of water and energy, especially for heating and chemical reactions, which also release air pollution. Another major issue is tailings. What's left after the metal is extracted. These leftovers can contain toxic substances that pollute soil and water, especially if not managed properly. So while metals get a lot of attention, we also mine a wide range of non-metallic resources. Sand and gravel are actually the most commonly mined materials worldwide, mostly used for making concrete and construction materials. Other important non-metallic minerals include gemstones, limestone, salt, and potash. These are essential for things like agriculture, water treatment, and even food and jewelry. So this map shows where some key mineral resources come from. Many are essential to modern technology and industry, like copper from Chile, silicon from China, and indium from Canada. But not all mining is equal. Some minerals, like cobalt from the Democratic Republic of Congo, are classified as conflict minerals because their extraction is linked to violence, exploitation, or environmental harm. This highlights the importance of understanding both where our materials come from and the conditions under which they are mined. So most mineral deposits contain only a small percentage of the desired material, which means large volumes of rock must be removed to access it. This leads to significant land disturbance and environmental damage, from habitat destruction to soil erosion and water contamination. The exact method used depends on the deposit, and we'll look at several types from surface mining to underground and placer mining, each with its own set of impacts. So strip mining is one of the most common surface mining techniques. It involves removing large horizontal layers of soil and rock called overburden to expose mineral deposits close to the surface. So once the resource is removed, the strip is refilled and the operation shifts to the next strip. While it's efficient for shallow deposits, it significantly disturbs land and ecosystems and can lead to erosion and habitat loss. So one major environmental issue linked to strip mining is acid mine drainage. When sulfide minerals and exposed rock come into contact with water and oxygen, they form sulfuric acid. This acidic runoff can flow into nearby waterways, turning them orange, as you can see in the photo here. So acid mine drainage harms aquatic life and can contaminate drinking water, making it one of the most serious long-term impacts of mining. Subsurface mining is used when minerals located too deep underground for surface methods. Subsurface mining is used when minerals are located too deep underground for surface methods. Workers dig vertical shafts and horizontal tunnels to reach and extract the deposits, often coal and precious metals. While this method reduces surface disruption, it comes with serious risk. Miners face dangers from gas explosions, collapsing shafts, and long-term exposure to coal dust and toxic fumes, which can lead to respiratory diseases. Subsurface mining doesn't just pose risk while active, abandoned mines can cause long-term problems too. One dramatic example is Centralia, Pennsylvania. An old coal mine beneath the town caught fire in 1962 and is still burning underground today. Toxic gases and unstable ground forced nearly everyone to evacuate, turning Centralia into a ghost town. It's a powerful reminder of how the impacts of mining can persist for decades, even centuries after operations stop. Open pit mining is exactly what it sounds like. It involves digging a massive hole in the ground to access minerals that are spread out evenly through large areas of rock. Along with the valuable ore, a lot of surrounding rock must also be removed. While it's efficient, this method leaves behind enormous scars on the landscape and can lead to habitat destruction, dust pollution, and groundwater contamination. Open pit mines are terraced to allow people and machinery to move safely around the site. As long as it's profitable, the pit can keep expanding, but in some parts of the world, mining conditions are far from safe. This image highlights the human cost, conflict, exploitation, and dangerous working environments are realities in many informal and unregulated open pit mines. It's a reminder that mining has not only environmental consequences, but serious ethical and social dimensions also. So this image shows just how massive open pit mining can become. That's because the valuable ore makes up only a small percentage of the rock. To access it, tons of surrounding waste rock must be removed. The result is a huge terraced pit that can span kilometers wide and hundreds of meters deep, transforming entire landscapes. So once an open pit mine is abandoned, it often fills with water, but the water can become dangerously toxic. When sulfide minerals are exposed to air and water, they become sulfuric acid which dissolves heavy metals. A real-world example is the Berkeley Pit in Montana. It's a former copper mine turned massive acidic lake with a pH of 2.2, similar to lemon juice. It's now one of the EPA's largest Superfund cleanup sites and a powerful example of long-term legacy of mining. Mountaintop removal mining is one of the most destructive forms of surface mining. It involves blasting off hundreds of vertical feet of mountain to reach underground coal seams. Before blasting, forests are clear cut and topsoil is stripped away. The leftover rock, called overburden, often doesn't fit neatly back into the mountains, so it's dumped into nearby valleys. This can clog streams, destroy ecosystems, and pollute water with acid mine runoff. Mountaintop removal doesn't just alter the landscape, it also accelerates erosion. This leads to more frequent mudslides and flash floods, especially in regions like the Appalachian Mountains. These risks have prompted the EPA to revoke permits and reconsider the use of this mining method due to its severe environmental and community impacts. Another method used to extract minerals is placer mining. This technique relies on the movement of running water to separate lighter materials from heavier metals and gems in riverbeds. You may recognize this process from historical gold rushes, but it's still used today. For example, in the Democratic Republic of Congo, miners use placer mining to isolate tantalite, a high density mineral critical for electronic devices. Placer mining may seem low impact at first glance, especially when we picture the classic image of gold panning in streams. However, it can have serious environmental effects. Disturbing sediments and waterways can destroy aquatic habitats and increase turbidity, which reduces water quality for both wildlife and people. The sediment can smother fish eggs and disrupt spawn areas. So while most mining takes place on land, it's important to know that some mining also occurs in the ocean. Seawater contains trace amounts of minerals like magnesium, and in recent years there's been increasing interest in extracting valuable minerals from the ocean floor. To do this, specialized equipment, essentially large hydraulic dredges that work like underwater vacuum cleaners, is used to collect mineral-rich sediments. However, this practice is not yet widespread. The logistical and environmental challenges are significant. Mining at such depths is technically difficult, energy intensive, and extremely expensive. Plus, we still don't fully understand the ecological consequences of disturbing deep sea habitats. For those interested in real world application, the link on this slide points to a news story that highlights emerging technology in deep sea mining and the debate surrounding its potential risks. So as we consider the future of mining, especially in the ocean, we must weigh both potential benefits and serious environmental trade-offs. Extracting minerals from the ocean might seem like a promising solution to resource scarcity, but we must ask, at what cost? The image you see here may be related to ocean mining. The image you see here may be related to ocean mining operations or conceptual technology. Researchers and engineers are developing new tools to reduce environmental impacts, but the ocean remains one of the least understood ecosystems on the planet. Disruption here could mean long-term consequences for biodiversity, fisheries, and even global climate patterns. This is why regulation, environmental assessment, and international cooperation are so critical in this space. The ocean belongs to all of us, and it's up to us to protect it. So after mining operations end, restoring the land is a critical step in minimizing long-term environmental damage. In the United States, the 1977 Surface Mining Control and Reclamation Act requires companies to submit a reclamation plan and cover the associated costs before mining permits are issued. This law ensures that mining sites are responsibly managed even after they're no longer in use. At the same time, scientific research is playing a big role in improving restoration. Scientists are working to develop plant species that can survive the poor soil and harsh conditions found at many reclaimed sites. These plants not only help reestablish vegetation, these plants not only help reestablish vegetation, but can also assist in treating toxic runoff like acid mine drainage. Together, regulation and innovation are helping us reclaim and repair mined landscapes. So, one of the oldest laws still guiding mining policies in the U.S. is the General Mining Act of 1872. This law allows any U.S. citizen to or company with permission to claim rights to mine on public land. It was originally created to support westward expansion and regulate mining during the California Gold Rush, but today many people argue that it is outdated. They say it essentially gives away public resources to private companies with very little return to taxpayers. Although there have been efforts to update the law, like the Hard Rock Mining and Reclamation Act of 2015, none have successfully made it through Congress. So, despite all of the changes in technology and environmental awareness over the past century and a half, this 150-year-old law still shapes much of how mining is done in the U.S. today. So, as we wrap up our discussion on mining, it's important to think not just about the environmental impacts, but also the long term sustainability of mineral use. Minerals are non renewable resources. Once they're gone for good, at least on human timescales. So, in addition to reducing environmental harm, we also need to use these resources wisely. One of the best ways to do that is by reducing waste and recycling minerals that have already been extracted. By recovering materials from used products like electronics, vehicles, and construction materials, we can help extend the lifespan of these valuable resources. Ultimately, moving towards sustainable mineral use means thinking ahead, using resources efficiently, and reducing our need to constantly extract more from the earth. So this chart shows how long key minerals may last in current use rates. Some, like lead and titanium, are abundant and expected to last hundreds of years. Others, like nickel and molybdenum, have much shorter economically recoverable supplies. While technically recoverable reserves are larger, cost and logistics make them difficult to access. That's why recycling and reducing waste are essential for sustainable mineral use. Estimates for how long mineral resources will last can change over time. That's because new discoveries, changes in technologies, and shifts in demand all affect availability. For example, when prices rise, mining companies may invest in better extraction methods, and economic trends also influence how quickly minerals are used, and higher prices can encourage more recycling. So right now, only about 35% of metals in the U.S. Municipal waste stream are recycled. By increasing this rate, we can significantly reduce the environmental impacts of mining and processing, and also cut down on energy use. Improving recycling is one of the most effective steps we can take towards sustainable mineral use. So these are the recycled minerals in the United States, and the United States recycling rate. So for gold, it's slightly less is recycled than is consumed. For iron and steel scrap, nearly 100% of vehicles, 88% of appliances, 71 to 98% of construction materials, and 70% for cans. And then when we look at lead, 71% consumed comes from recycled post-consumer items. Nickel, 52%. 52% consumed is from recycled nickel. For zinc, 25% produced is recovered, mostly from recycled materials used in processing. And then we have them for copper, aluminum, tin, and germanium. So this is a continuation of the recycling table. That some minerals like molybdenum and cobalt are being recycled at modest rates around 30%, but others such as silver, bismuth, and industrial diamonds still have very low recycling rates. For example, only 2% of industrial diamonds come from recycled materials. So these figures highlight the opportunity we have to improve recovery and recycling methods to reduce dependence on newly mined resources.